Okay, briefly, we built up a matrix A from the intended reduced version of A, okay? And I thought I'd made an error in it because I'd made an error someplace else that led me to believe there was an error. That's kind of interesting, but in any case, I have a big question mark here. I can erase that. I'm confident of my, I wouldn't bet my life on it, but I bet a lot of money on it. I'm confident that everything here is pretty much right. Okay, so I'm claiming then, and I built this matrix up just by adding rows of this and just doing row operations on this till I got this. So I can reduce this by those inverse operations to get this, so I know this reduces to this if I did my arithmetic right. Basis of the row space we see to be, well, the 3 rows of the reduced matrix, we know that. And basis of the column space, well, each column that corresponds to a leading 1 from a row, if you go down to the original matrix, that column is a basis vector for the column space. So the column space, well, the columns have, the columns corresponding to the leading ones of the rows are these. So the column space is going to be these 3 rows, and that's what I've written down here. The dimension of the column space has to be the same as the dimension of the row space because every row has a leading 1, and every leading 1 gives you a column. Okay, well, that's kind of a review. So what we're really interested in is null space. And I said that the null space is the set of all vectors that give us 0. Okay, well, that's a little vague. So here's a more specific statement. It's a set of all vectors x such that ax is 0. That's what we mean by gives us 0. So it's a set of all vectors that give us 0, a set of all x's that satisfy this equation. Okay, so well, how do we solve the equation ax equals 0? Well, we write down the A matrix, and we write down a row of zeros, and we get a matrix that represents the set of simultaneous equations that you get if you write out this system. Okay, so we reduce this, and we get the solution. Another way of representing this augmented matrix is just A with a vertical line here and the 0 here, 0 vector. Well, we did that. And we got, well, when we reduce it, clearly this is still going to remain a row of zeros. No row operation is going to change any of these zeros over here at the in the augmented part of the matrix. And we get this matrix so that our system, whatever the system was when we did this, what would it be? x1 plus 2x2 plus 1x4 plus 1x5 equals 0, 3x1 and so forth, okay? Reduces to this, so that system simplifies to this. Then, what's the solution to this system? Okay, well, x5 is 0. Now, we have x3 plus 3x4 equals 0. I'm going to let x4 be one of my 2 free variables. We get 2 free variables because we've got 3 equations and 5 unknowns. So x4 is going to be one of my 3 variables. So x3, of course, from this equals negative 3x4. We let x4 equal s. That's our first free variable. We're going to let the letter s stand for that free variable. Then x3 is negative 3s. Okay? Then first equation becomes x1 plus 2x2 plus s equals 0. Okay? Well, we still have 2 unknowns here and only 1 equation. This is the last equation we've got. Out of the 3, we've already used this one and this one. So we have to have another free variable. We'll let x2 be that free variable. Let x2 equal t. Then this equation becomes x1 plus 2t plus s equals 0. And it follows that x1 is negative 2t minus s. So now our solution to this equation, general solution, x, is going to be, well, x1, x2, x3, x4, x5, but substituting for x1, x2, x3, x4, and x5, we get negative 2t minus s, t, negative 3s, s, 0. That's the general solution to this equation. So this is the general form of a member of the null space, of a vector in the null space. Well, I can do more. I can break this into the part that depends on t and the part that depends on s. So I just write down the negative 2t, the t, and then nothing else depends on t, so I'm just writing zeros. Okay? And I can write the negative s and the negative 3s in this position in this, and the s here, and zeros in the other position, because there are no s's in the second and fourth position here. Now, what does that accomplish? I'm saying that this equals this. Well, you can think about it, but just add these two and see that you get this. Negative 2t minus s is negative 2t minus s. T plus 0 is t, etc. Then I factor out the t here, I factor out the s here, and what do I see? I see that, okay, any solution has to be of this form, which means it has to be of this form, which means it's some multiple of this vector plus some multiple of this vector. T and s are free variables, they can take any value. So it follows then that these two vectors are basis for the null space. Well, that's really pretty cool, but there's something even cooler. Okay, so I'm going to include that here. Now I'm asserting all this. We haven't defined or proven the dot product, but I'm going to define the dot product of two vectors, okay? Now I've got the dot product of this vector and this vector. So you write the vector, you write a dot, you write the other vector. Now this happens to be one of the vectors in the basis of my null space, that's the first one, and one of the basis vectors in my, well, one of the vectors, any vector in my row space, but I chose the first one, okay, the first row. So this is just the first row of the row space. Well, I do the dot product, very simple. Multiply these two, negative 2 times 1. Multiply these two, 1 times 2. Multiply these two, well that's 0 times 0. Multiply these two, it's 0 times 1. These two, it's 0 times 1. Add those up, just as if I multiplied this as a row times this as a column. So it's almost the same as multiplying a row by a column. And when you do multiply a row by a column, you're actually doing the dot product of the row with the column. Well, we see that this adds up to 0, and that has very profound implications. Okay? Vectors are said to be orthogonal if and only if their dot product is 0. Okay? Now, orthogonal is a generalization of perpendicular. It's easy to prove because in our two perpendicular vectors have negative reciprocal slopes. It's easy to prove that their dot product then has to be 0. Okay? And they aren't perpendicular if they don't have negative reciprocal slopes. So vectors that are perpendicular in R2 are also what we call orthogonal. In R3, you can do the same thing, but you can't do quite as easily with the negative reciprocal slopes. Orthogonality goes way beyond perpendicularity, though. It's a very general concept, but you think of it as something very akin to perpendicularity, and in R2 or R3, it does mean perpendicularity, just as we understand perpendicularity, right angleness. Okay? Another thing we can do with the dot product, incidentally, is, we'll come back to that. Okay, stick with the idea of orthogonal. We just showed that this vector is orthogonal to this vector. If I did my calculations right, it had to be. Now, you don't want to try to prove that at this stage of your education, although you probably could, but it would take a while. Either of these vectors is orthogonal to any row vector, or to any row vector in this matrix, or in any matrix that we can get by reducing A. Okay? And this says, okay, either vector in the null space is orthogonal to any row of A, any vector in the row space. Any vector at all in the row space, doesn't have to be any of these or any of these. Any vector at all in the row space will be orthogonal to any vector in the null space, it turns out. So we say that the null space is orthogonal to the row space. That's a huge, big deal. You won't appreciate that yet, but it's really a big deal. It's really kind of a neat idea. even if you don't understand what a big deal it is. Okay, just a couple other things about the dot product. The magnitude of a vector is the square root of its dot product with itself. And we denote that by kind of an absolute value sign with attitude, kind of a double absolute value sign. And then the statement, this just says, again, that the magnitude of V is V dot V. It's the square root of V dot V. Okay, or the square of the magnitude of V equals V dot V. And this is just an extension of the Pythagorean theorem. I'm not going to detail that now. We probably will see that because it's actually quite easy. Okay, so that's a whole lot of mileage out of this one example.